Okay, so today we're going to be looking at permutations of n objects with repetitions and then with restrictions. So say we had n, oh, why is this not working? There, it's working now. So we had n objects, but there's repetitions. So not all n objects are distinct. Therefore, there's going to be fewer than NPN permutations. So we need to do an adjustment to the factorial function. Now let's consider A, B, C, D. But we're going to write this one with a different colour, just to make it clear that it's different. There we go. So we can write them like this, but we can also write them like that. But that's the same. A and A is actually the same. So we can do but again, A and A is the same. So if we're swapping the A's over, we're going to get the same arrangement. Now, when we've got repetitions, first think, what would be the arrangement if there were no repetitions? So, if the 5 letters were distinct, we would have 5 factorial arrangements, which would be 120. But the number is reduced by, the number is reduced to half, or 1 over 2 factorial, the total arrangements, because of the 2 repeated letters. Now, we can write this as the number of arrangements. Oops. Would be this 2 factorial is important. It's not just going to be half. We're going to see in a minute for the general rule. But for this example, we could have the number of possible arrangements is reduced to 60. Now, the general rule for this is the number of permutations of n objects of which P are one type, Q are another type, R are another type, and so on and so forth, is going to be equal to NPN, so the n number of objects, just like we'd have before, so it'd be n factorial, but then you divide it with P factorial times Q factorial times R factorial times so on and so forth. So that's n factorial over p factorial times q factorial times r factorial for as many different numbers of objects you have, where p plus q plus r and so on is equal to n. So let's do an example of how this actually works, because it can look like just a load of letters, but when you look at them in an example it can become clearer. So the capital of Burkina Faso is, now I hope I pronounce this correctly, Ouagadougou. I'll write it down. Ouagadougou. Now, written in capitals to make it clear the different letters that are in it. Find the number of distinct arrangements of all the letters. Well, let's first find out how many letters are in it. There's 11 letters. Now, how many O's are there? There are 3 O's. There are, how many U's are there? There's 3 U's. A's, there are 2 A's. And G's, there are 2 G's. And there's 1 D. Correct? Yeah, 1 D. So, the number of arrangements is going to be n, which is 11, factorial times 3 factorial times 3 factorial times 2 factorial times 2 factorial times 1 factorial, which equals 277,200 different arrangements of the letters. So now we're going to go on to permutations of n distinct objects with restrictions. So the number of possible arrangements is reduced when restrictions are put in place. As a rule, find the possible arrangements without restrictions first. And then that'll give you a point to begin your investigation, and you will then be able to use that as a benchmark, and also to then deduct the restrictions from the possible arrangements without the restrictions. We'll see how that works with our examples. So, first things first, let's do an example. So we're going to find the number of ways of arranging 6 men in a line so that the oldest is at the far left, the two youngest are at the far right, and finally the shortest is neither at is oops, I should put an at, is at neither end of the line. Excuse the very messy handwriting. So, without restrictions, we have 6 men, and the possible numbers of arrangements is 6 factorial, which is 720 ways. So there must be, once we add in the restrictions, we must have an answer that is less than 720 ways. So if we have the oldest man at the far right, so let's think about so here's 1, 2, 3, 4, 5, 6. Here's our 6 different positions. Now the oldest man is at the far left, so he's here. So he has to be there. There's only one way we can arrange that one man in that one position. So we can put him here. But the rest of the other 5 men can be in any of the other 5 positions. So we have here the different men and 5 men being arranged here. So there would be 1 times 5 factorial, which is 120 arrangements. Now B, the 2 youngest men at the far right. So again, let's think about the far right. So here we have these 2 men here, 1 and 2, and they can be swapped round between their positions. So there's 2 ways of arranging these 2 men, and on the rest, 1, 2, 3, 4 men here, and these can be arranged in 4 factorial ways. So here we have times 2p2, which is 4 factorial times 2 factorial, which is 48 arrangements. And finally, let's clear that bit away. We have the shortest is at neither end of the line. So there are only 5 men who can be placed at the far left. So there are only 4 men that can be placed at the far right. Or you can switch that over. You could have 4 men here and 5 men here. And so in the middle, you can have, but in the middle places, you can have 5 men. Or 4 men, sorry, because you've got the 4, yeah, 2 are placed here. So that would be, so you can have 4, 3, 2, 1 are the remaining men. So in the middle here, there's 4 men being changed around. Here you can have 5, but there's only one position, so that position can change 5 different times. So you can have 5 different men. So it's just 5 ways of changing this position, and this position changes 4 ways. But just to note, you can have these and you can just switch these over, but it doesn't change the maths of the problem. So that gives us 5 times 4 factorial times 4, which is 480 arrangements. Another way of doing this is to consider that the shortest man can be placed in one of 4 positions. So the shortest man can be placed in one of 4 positions. And the rest of the 5 men can be placed anywhere. So that would again give us 480 arrangements. Let's get rid of that as well. So let's do another example. How many odd 4-digit numbers greater than 3,000 can be made from the following digits: 1, 2, 3, and 4. So the restrictions here are going to be placed on the thousands column and the units column, because it has to be odd and it has to be greater than 3,000. So we're going to split this up into 2 parts. We're going to start with numbers that are with the thousands column having 3,000s. So let's start with 3 in the far left, or the thousands column. So we'd have 3 here. So there's only one way of putting 3 here. And the only other odd number here is a 3, so we have to have, is a 1, sorry, so we have to have 1 in here. So that's only one way of choosing that. And so here, the 2 and there's 2 and 1 here, and they can alternate. So we've got two objects switching around here. So this gives us 1 times 2 factorial times 1, which is 2 numbers. So let's now have 4 in the thousands column. So again, we've only got one way of choosing this, and this time we can have 1 or 3 here. So there's 2 ways of choosing there's 2 numbers that can go in the units column. And here we have, again, the last 2 here. So here we have 1 times 2p2 times 2, which comes out at 4 numbers. And now we can add these together. Therefore, there are 2 add 4, 6 odd numbers greater than 3,000. One last question. Find how many ways 2 mangoes and 3 watermelons can be placed in a line if the 5 fruit are indistinguishable or distinguishable. And the mangoes are, firstly, must not be separated, must be separated. So let's think about, let's put mango 1 and mango 2 here. Then we've got watermelon 1, watermelon 2, watermelon 3. Now what we can think about is, firstly, these 2 mangoes, they have to always be together, but we can switch them round their position. So mango 2 can go here, mango 1 can go here. So here we have 2 ways of ordering the mangoes. But because they have to be kept together, we can think about the mangoes as a single entity interspersed with the watermelons. So this is like saying we've got 4 objects. So the number of ways that we can distinguish them is going to be 2p2 times 4p4, which is 48 ways. Now, if they can be separated, let's think about how many ways, if there was no restrictions, there would be 5p5, which is 120 arrangements. Now, all these 120 arrangements, that's giving no restrictions. Now, let's think about these 2 statements. The mangoes in the first case, they must not be separated. In the second one, they must be separated. These are 2 exclusive statements. That mangoes either are or they aren't separated. Now, if there's 120 ways of arranging all 5 items of fruit, we can take the 120 and subtract the 48 ways that we have of ordering the fruit where the mangoes are together. And that would give us the 72 ways of ordering them when the mangoes are separated. Because they're either separated or they're not. And we know that this is when they are not separated, so this must be when they are separated. I think I said that right. So I hope that makes sense.